Greetings to you all. We're continuing with our lessons on photovoltaic. Your lecture being Dr. N.E. Mabunda, professional engineering technologist. This lesson will be focused on AC energy sources, circuits, properties, and signal analysis, with an objective to give you knowledge about RLC circuit, being resistor, inductor, and capacitor networks, configured either in parallel or series. We will further your studies by looking at power factor and its correction, where this has got a significance of showing the relationship between true power and what is imaginary, that you pay for it, virtual power, or in other words. The signals we receive domestically, quite often they are AC signals being easy to transmit, but they're not following a smooth path as they face reactance, which is an opposition to the flow of current. If we have two lines in parallel, since they represent conducting plates, in between you might have what's so-called parasitic capacitance, where at higher frequency it will short out your line. Again, with one wire running, it may act like a coil that become an inductor, which will create an opposing resistance to the flow of current. These occurrences of reactance, it create unnecessary expenses to the system. Inverters are not exception. They are affected by reactance. You design a solar system where you size batteries, inverters, and solar panel. It happened that now when you load your system to perform over a certain load, it's somehow not doing what is expected. And the problem might be that the perceived load is higher than what it is given as the rating, which might result from inductance or capacitive. Imagine now you're running a LED light which is written 5 watt, but when you observe the current, it somehow reflect that may be given by 100 watt. So your system won't perform as expected. With that, now we see it important to have a closer look at RLC circuit. First, we look at the vector diagram for a parallel RLC circuit. Now, we're gonna be talking in terms of current when we look at parallel circuit, where IC is from the origin on the vertical axis, it moves up, and IL on the horizontal axis, it moves down. R is perpendicular to both of them, moving along with the x-axis. As a result, now, to get the net sum of the vertical axis, you will take the difference of the two, where the smaller is subtracted from the bigger one. You square it following the theorem of Pythagoras, because if you look at this area, we've got a right angle triangle, and you add it to the square of the adjacent. So that will give you the square of the total reactance, which is called Z, or total impedance. So to work out total current, you can follow the same conversion. But it's important to note that the angle between inductive reactance or inductive current and capacitive reactance or capacitive current is 180 degrees. Both inductive and capacitive are 90-degree phase change with the resistor. We look at the example here. There is special frequency which, when it occurs, XC happen to be equals to XL. Putting the right equations of WL or XL rather and XC, we come up with the FR, which is equals to the reciprocal of 2 pi the square root of LC. That's when it's in we were got parallel. So, but that I must warn you that is more of an approximate a way to calculate it in a case of parallel. Now, having XL to cancel XC, it means the remaining part of reactance is R, which is 1 ohm. Now, here they wanted to calculate at resonance the RMS current. So this is a peak voltage. You need to calculate, make it an RMS voltage. You divide by square root of 2. Hence, you see the square root of 2 there. Then once you make it RMS voltage, you can calculate RMS current by following Ohm's law. For sure you remember that. V R I. When you want I, it divide onto V by R. So it gives you roughly 8,5 amps. Now, visually, what can we see on an oscilloscope? We make assumption here because we're not plotting this signal. We find it down. So a logical assumption will be that if you've got the supply and a component which is connected to the supply will be at a higher voltage. Now, if we look at our reading, channel A is giving around 8 volts. But then, and the same channel A is at 5 volt per division, meaning that each division is 5 is 10. Right, so the one which is close to 10 is the 7 one. So that one we call it channel A as the supply. Then the remainder, which is at 10 millivolt per division with a maximum of 6,5, roughly 6,6 millivolt. It will be the output channel B, where the output can be taken from the resistor or it can be taken from the combination of capacitor and a resistor. But after all, what we need to emphasize that is between in any of the output and the input signal, there is a phase difference. Now, how do you observe that? If you look at the peaks there, they are separated by an amount of 0.5 divisions, which is occurring out of possible 3 divisions for each signal. So 0.5 over 3, and then 3 being 360 times, it's a prorata of 360, which is gonna give you about 60-degree phase difference. Now, in series, what happened? We talk in terms of voltage now. When we talk series, we no longer talk about current, but yes, the resultant will still be obtained by using theorem of Pythagoras. One other thing to note is that XL and XC have swapped position. XC now occur at the bottom, XL is at the top, where it goes with VL, and the bottom one goes with VC, and across the resistor it's going with the horizontal axis. Now at resonance, the equation is equals to 1 over 2 pi the square root of LC. Here is giving us 1 kilohertz. So we use the old type of equation where it's more accurate for this instance. And now, to find the total impedance by the reactive component, you take XL minus XC, which is 0. Then the resultant is R, and then you convert the peak of 12 volts to RMS divided by 1. Now, an interesting phenomena here is that the voltage across the inductor, it has been magnified more than the supply, 51 compared to 12. So resonance in series can create voltage amplification or magnification, to use a proper term. Now again, they came to visually. Now what do we see? Here we're talking about voltage, but we know that the biggest, it's in the inductor. So the 50 volt per division, we can give it to the inductor, 1 division. So we'll have to stick to that. If we say, and maybe we have to look at the other one, 5 volt per division, we say is the supply. So we say this one is 5 volt per division. 2 division will give us close to 12 volts. It's fine. 2 divisions, and then the other one is 50 volt per division. 1 division will give us 50 volt. And there is one thing which you need to check as well, the time per division. So there is your time per division. Actually what it means is how much millisecond do you count when you move across. That you get a period which you take a reciprocal and get a frequency. So that's how we analyze signals on the oscilloscope. Then the power factor, the power which you account for, but it's not doing a useful job. What I mean by that, you pay for it, but it's not benefiting you. So an analogy here is you buy a beer. Unfortunately, I don't drink. They say a glass of beer, but then the beer only goes there and leave about 20%, which is foam. That 20% you pay for it, but you won't use it. It's virtual, it's not a liquid itself. Now, if we look at the equation for impedance, Z is equals to R, and the y-axis is denoted by J, the difference between the capacitive reactance and inductive reactance. So then the real power is on R. That one gives, the virtual power is what is given by Z. So meaning that the ratio of the power on the resistance, which is I squared R, is the equation for power across the resistor, and VI for everything, it will give you the power factor. If it was only a resistor, VI and I squared R will be the same. But now, it's not the same because we have got inductive. So now, if we look at this angle, if a resulting voltage is forming 60 degrees with the x-axis. The power factor, that ratio, which is just adjacent over hypotenuse for 60 degrees, we'll just take a cos of an angle. Mathematically, it will give you 0.5. That's it, folks. We came to the end of our lesson. Like as usual, let's recap and see if we completed all our objectives. We look at RLC both in parallel and series, so that is simply covered. We can tick it off. We did power factor right now, looking at the cos theta angle formula, or I squared R over V over I. So everything has been covered. Thanks for watching, and stay alert for more courses which are to come. Good luck. Bye bye.